In this video, we're going to look at all the components of a hypothesis testing. And similar to confidence interval and hypothesis testing, the formula we use uh, is depending on what it is that we're testing. And for population mean, it depends on if we have population standard deviation given or not given. So we're going to look at example of a hypothesis testing, a full problem, but specifically we're going to look at population mean when population standard deviation is known in this video. Okay, but the main structure of hypothesis test is all similar. We follow this. All the components are very similar for all the testing. It's just that we use different formula for one part. So we already looked at how to state the new and alternative hypothesis and how to come up with an interpretation of a conclusion given if we reject, not reject new hypothesis. So we looked at beginning, the setting up part, and the conclusion part in earlier video. So today we're going to look at how to calculate test statistic, which will give us the p-value, which can help us find the conclusion. Okay. So it follows all these steps. So let's look at what test statistics is first. Test statistic will be used to determine by the test we're performing. We need to always ask this question: are we testing the mean or are we testing the proportion? And that we can determine by reading the problem carefully. It depends on which type we use different test statistics, essentially different formula. For example, if we're testing the mean, population mean, and we know the population standard deviation, we use this formula to find test statistic. Okay. And here, X bar is the sample mean, population mean, this value is stated in the H naught, new hypothesis, sigma is the population standard deviation, and N is sample size. Okay. So we found a test statistic, which case in this case will give us the Z value from the Z table. And using the Z table, we can find the p-value. Okay. P-value is the probability that the test statistic will take on a value as extreme or more extreme than the observed test statistic. Okay. So in general, the smaller the p-value, the more evidence we have against the null hypothesis. Smaller the p-value, the more evidence we have against the null hypothesis. Okay. So the way we calculate p-value is find the test statistics, as I use the formula in this case, this formula will give a z value, and we're finding the p, which is essentially finding the probability. And this is why the left tail, right tail, two tails is very important. If it's left tail, we just find the probability of z smaller than the test statistic we find, looking at the z table. If it's right tail is greater than, which in that case, it'll be 1 minus probability of z less than test statistic. Test that, let's say. Because it's area right side, we have to do 1 minus area left side. Since the z table only gives us the area left side. Now for two tail, we have to do 2 times probability of z greater than absolute value of a test statistic. So if test is negative value, we have to take the absolute value. So the way we think about this is 1 minus, let's do this way. Sorry, let's multiply 2 times just this portion greater than test statistic is same as 1 minus probability of z less than absolute value of test statistic. Test that. Test that. So for two tail, we have to find 1 minus z less than absolute value of test statistic and multiply by 2. Then we get the area. If the normal graph, we're finding these areas. Right? Okay, and so using these three, one of these three method, we can determine the p-value. It will give us a probability. And if that p-value is less than given alpha, alpha is the level of significance we discussed earlier. If less than alpha, then we reject the new hypothesis. So let's look at a problem together to practice all these. Okay. Jan to Ben is a Morgan horse at Colorado Dew Ranch. Over the past 8 weeks, veterinarian took following glucose reading from this horse. And here, 1, 2, 3, 4, 5, 6, 7, 8. So n is 8. There's a sample 8. The sample mean is 93.8. Let x be the random variable representing the glucose reading from Jan to Van. We may assume that x is a normal distribution. We know from the past experience that population standard deviation, very important, because if this is not given, we have to use something else, which we'll look at later. But here, population standard deviation is given. The mean glucose level for horse should be, population mean should be 85 milligram per 100 milliliter. Do these data indicate that Gentle Vans has an overall average level higher than 85? So here the question is, they should have more than 85. But does this data indicate otherwise? That's what it's asking. Okay. So let's set up the null and alternative hypothesis. So null says their population glucose level should be bigger than 85. So the null hypothesis can be either equal to 85 or less than equal to 85. I'm sorry, it should be 85 on the right or 80. So just looking at this portion, we know this is right tail test. Again, this is very important. We know the right tail test because that will change the way we find the p-value later. And let me also note the one thing. This number here, we're referring to the population mean value. Okay? So, let me say it again. They're asking, this is the question they're asking. This is their alternative hypothesis. Do these data, the sample data, indicate that their glucose level is higher than 85? That's why we put this in the alternative hypothesis. A null hypothesis is opposite or unchanged. So either equal 85 or less than equal to 85. Okay. This is alternative hypothesis, right tail test. Okay. So once we find this, we set up the statements, then we find the test statistic. Test stat. Now this is the where we have to go to the formula sheet and pick the correct formula. So here we're testing the mean glucose level. And since population standard deviation is known, we have to use this formula to find the z value. So let me copy the formula. Z value is the z value formula. Again, it's very important to use correct formula. So we're using z. Okay. That's because population standard deviation is known. This is known. And it's also written in the formula sheet. So here, sample mean, they said sample mean was 93.8. 93.8. Minus, this mean is population mean. Don't confuse this mean. That order is also important. Divide by population standard deviation is 12.5. Divide by square root of sample size n. And if you calculate this, it gives you 1.99. So we know that our test stat is z equals 1.99. So now we're going to find p-value using this. P-value. Well, since it's right tail test, p-value lowercase p is probability of z greater than test stat. Well, in this case then p z greater than 1.99. But area right side is not directly given in the z table, which is why we have to do 1 minus probability z less than 1.99. So from the z table, we find this from the table, z table. We can find this probability value. So let's look at the z table together. 1.99. Oops. Here's the z table, and it was 1.99. So it is right here. 9767. 0.9767. So what that gives us, 1 minus 0.9767 is 0.0233. So our p-value is 0.0233. That's a p-value. So for conclusion, we ask, is p less than alpha? So we look at the problem alpha, they use 0.05. So in this case, is p less than 0.05? Well, it is, right? 0.025, 0.0233 is less than 0.05. Yes. If p is less than alpha, if this is true, we reject h naught. Reject h naught. If it was otherwise, if p was greater than alpha, we fail to reject h naught, or we do not reject h naught. Remember the way we think about conclusion? Think as we have h naught, h1. Either we reject this or don't reject this. Since we reject this, that means there's enough evidence to support this one. Since we rejected h naught, we have enough evidence to support h1. So let's write the conclusion here. There is sufficient evidence. There is means because we reject h naught. Evidence to support that Gentleman's mean glucose level is higher than 85. Again, this portion we always just rewriting null hypothesis, alternative hypothesis in words. We're always writing alternative hypothesis in the context of the problem. That doesn't change for conclusion. We always write this as a final conclusion. Either we have enough evidence to support H1 or we don't have enough evidence to support H1. Okay. Let's look at another example. Sunspots have been observed for many centuries. Records of sunspots from ancient Persia and Chinese astronomers go back thousands of years. Some archaeologists think sunspot activity may somehow related to prolonged period of drought in southwestern United States. Let X be a random variable representing average number. So we're dealing with the mean. Okay, this is important to recognize. We're doing mean observed for 4-week period. The random sample of 40, this is n equals 40 then, from Spanish colonial times gave sample mean x bar of 47. Previous studies of sunspot during activity during this period indicate a population standard deviation of 35. So sigma is 35. It is thought that for 1,000 years, the mean number of sunspots for 4-week period is about mu population mean equals 41. Sunspot activity above this level may or may not be linked to gradual climate change. Do the data indicate the mean sunspot activity during the Spanish colonial period was different than 41? So because it's different, we let you know it's going to be two-tailed test. But first, let's write the statements. And let's say use the 0.05, alpha 0.05. So first, we always find the null and alternative hypothesis. And what they want to know, alternatively, what we're testing is mean differ from 41? Population mean different from 41. Okay. And then opposite of this is 41. So in this case, there's only one way to write null hypothesis. And here we know this is two-tailed test. Different from 41. Do the sample data we collected show enough evidence that the population mean is actually different from 41? That's what we're testing here. So then let's find the test stat. Remember, for test stat, it's very important to identify if it's Z or T. Since population standard deviation is known, we use Z. Otherwise, we have to use T, which we'll look at later, but for now we use Z. So then formula for Z is population sample mean minus population mean divided by population standard deviation over square root of n. So here, sample mean was 47. And this right here, this is always value we write in null hypothesis, or alternative 2, of course. So both are mean values, right? This is sample mean, population mean. So make sure to not confuse by these two mean values here, okay? So 47 minus 41 over population standard deviation was 35 divided by square root of sample size of 40. There are 40 sunspots. So this value gives us 1.08. So we have test stat equals 1.08. That's a test statistic. Once we find the test statistic, what we do is we find the p-value. So again, p-value, it changes, depends on two-tail, red tail, right tail. Here we're doing two-tail. So p-value for two-tail, we need to remember this, is 2 times. You can think of, since it's 2, you multiply 2. And it's probability of z greater than absolute value of test stat. And I'll explain why it's greater than and why we're multiplying 2. So essentially what we're doing is, here's a normal curve. Since it's different, right? Different means it can be either greater or less than. It can be either greater or smaller. That's why we're finding both of this area, either greater or less than from the population mean. Okay. So we're finding actually this area, and because of the symmetry, we multiply 2 to get both of this area. That's what we're finding greater than. Find this area and multiply by 2. And if z is negative, we need to take the absolute value. But here it's positive, so it doesn't change. So 2 times probability of z greater than 1.08. Absolute value of positive is absolute value. Well, then we cannot find greater directly, so we have to do 1 minus probability of z less than 1.08, like this. So we can find this value from the z table. So from z table, 1.08. 1.08 is 8599 right here, 8599. So what we're doing here, then we have 2 times 1 minus 1.8599. 2 times, if I subtract this, I get 1401. It gives me 0.2802 because I have to multiply by 2 for the final p-value. So p-value we get, p-value is 0.2802. We got the p-value. So then once you got the p-value, the fourth step is we compare, is p less than alpha from the given alpha? The alpha in this problem was 0.05. The alpha is always given in the problem. They use the alpha 0.05 right here. So it's p-value we got. The p-value we got was 0.2802. Is this less than alpha? Compare these two numbers. Well, this is actually bigger, right? So this answer is no for this problem. P-value is not less than alpha, or p-value is greater than alpha. Maybe let me do it this way. The question is this true? Answer is no, because 0.2802 is greater than 0.05, comparing two numbers. So this is not true, false. That's why I said no. Therefore, we do not reject, or let's say fail to reject H naught. Fail to reject H naught. That means, let me write the final interpretation here. There is not sufficient evidence to conclude that the mean sunspot activity was different than 41. Again, this I'm just writing alternative hypothesis in words. Okay. So two main things we looked at this video in terms of hypothesis testing is how to find test statistic and p-value. And again, all the structure for whatever we're doing in terms of hypothesis testing always follow this structure. The main difference from problem to problem, depending on the mean proportion, depending on population standard deviation given, not given, the formula we use for test statistics is different. But once we find the test statistic, the way we find p-value is same using one of these. And we find the conclusion is also same, comparing p-value with alpha right here.